Hi, hello everyone. So the title of our presentation is Electromagnetic Stress Tensor in Ponderable Medium. I'll first start by explaining electromagnetic stress tensor in the vacuum, which is also known as Maxwell stress tensor. To start with the derivation, let's first consider conservation of energy. Now for a single charge q, we know that the total Lorentz force is q E plus V cross B. Clearly the magnetic term is perpendicular to the velocity, so it will not contribute to the total work done. So we can write the rate of work done for single charge q to be q v dot e, where v is the velocity of the charge. Now consider a charge distribution, which is a continuous distribution. For this it can be easily generalized to j dot e and the integral over a volume. This power represents a conversion of electromagnetic energy into mechanical or thermal energy, which must be balanced by a corresponding rate of decrease of the electromagnetic energy within the volume. We can also see this in a way by using Maxwell's equation. We know J is equal to del cross H minus del E by del T, and then we further use the vector identity mentioned here to get the following: del dot E cross H plus E dot del D by del T plus H dot del B by del T. Now the second and third terms on the RHS might seem familiar as the energy, and that is the case. To proceed, we need to make these two assumptions. First of all, our medium is linear. What this means is that the response of the medium to the E and B fields is linear. That is, the polarization P and the magnetization are go like E or B, no higher order powers as we saw in photonics. So, and the other assumption that we make is that E dot D plus B dot H by 2 represents the total electromagnetic energy density even for time varying fields. Using the above two, we can write our rate of loss of power in the following way. And since in the start the volume that we considered was arbitrary, we can obtain a differential form of the above. Del U by del T plus del dot S is minus J dot E, where S is the famous Poynting vector known as E cross H. Now the physical meaning of the above is that the time rate of change of electromagnetic energy plus the energy flowing out is equal to the negative of the total work done by the fields on the sources. This is our usual statement of conservation of energy written in terms of a continuity equation. Now the form of it written in a continuity equation is what is very essential to us, because we are all familiar with continuity equation for suppose mass, charge density and other things, but when we write energy conservation in terms of continuity equation, we kind of get an interpretation of momentum flowing out of a surface, and this gives the idea of a stress energy tensor that we want to construct. The main idea of this section was writing the conservation of energy in a differential form, in a differential formulation, and identifying the Poynting vector. After this, I'll we can also see how the energy is flowing out by looking at the total mechanical energy of the system. Now, as I mentioned, J dot E is the power of the work done by the electromagnetic field on the sources. This must go into increasing the energy of the particles. So dE mechanical by dt is equal to integral J dot E d cube x. Now, for the combined system, we can use Poynting's theorem as showed above, and we can obtain dE by dt for the whole system is flux of the Poynting vector, where E electromagnetic field energy is E square plus C square B square by 2. Right. So we saw the energy conservation through Poynting theorem. Now I'll pass on to Gopal, who will go to momentum conservation, and then finally merging both of them together to get the stress tensor for vacuum. Right. So after having looked at the stress tensor part, we now look at the consideration of forces in a ponderable medium in presence of electromagnetic fields. Now, the property of forces has been a very long debate and controversy for a long time, and the route that the paper goes through and what we'll discuss is treating the magnetization density of a material as an Amperian current loop. We review the process that the paper, not the exact the same paper, but the previous few papers used to calculate the force on a force of electromagnetic field on M. Computing the total electromagnetic force, in addition to the force exerted on M, you also need to consider the force density on the induced currents, which is del P by del T cross P, where P is the polarization density. And one extra term which we'll mention later is due to the hidden momentum of the fields. Right. So I'll overview first how to derive the force on a magnetized slab with magnetization M in presence of E and B fields. Right. So we start our system is a magnetization with components mx, my, mz at a given point in space and is subjected to Lorentz force of the local B field. Right. So we model this magnetization in the Amperian current loop formulation. That is, we consider a loop with some current I circulating around a small loop of area delta square, and it produces some magnetic dipole moment I delta square, where n hat is the unit vector perpendicular to the loop surface. And we can define a number density of the loops, an equivalent number density to define the whole magnetization. Right. So the picture looks something like this. You can see there are three loops here. Why the three loops? Because we want three different magnetization components, and each of the loops gives us magnetization in one of the three Cartesian directions. Now, when we have these loops, then it's very easy to calculate the Lorentz force on them, and the expressions for them are listed in 1a, 1b, 1c. The key part is summing these up and then combining them into a single expression, which gives us a nice expression in the form of 2 m dot del cross b plus m dot del b minus del dot mb, del dot bm. And the last term is 0 because of Maxwell's equation where divergence of B field is 0. Right. And we can also write B is equal to mu naught H plus M, where a certain fraction of the B field is in the magnetization. So finally we get 3A. M cross del cross H plus M dot del H. Right. Note that this force is under the condition that there are no transient E and B fields in the system. That is, it's a steady state force. So we have to include the hidden momentum force finally in this, which we'll come to later. Right. So now we have the magnetic force ready. Next, we look at the force on the polarization was already discussed. That is the del P by del T cross B term. And as I mentioned, for problems that are not in steady state, we must augment the above two force terms by an additional E cross M by C square term to account for the hidden or intrinsic mechanical momenta. The actual derivation of this comes from quantum electrodynamics, and we felt it to be far too beyond the scope of this paper. But we can think of this in terms of coming from the momentum carried by the E and V fields, and the rate of change of that is giving an additional force, which we cannot directly get from Lorentz force. So the final equation that we get is by adding that del P by del T, we get this equation 1 as the final force expression, which we'll use to calculate the stress tensor ponderable medium. Thank you.
Now we are going to consider the conservation of momentum of a system of charged particles and electromagnetic field. So we want an equation similar to what we got in the case of conservation of energy. That is, we want rate of change of momentum plus rate of change of momentum of rate of change of mechanical momentum plus rate of change of electromagnetic momentum is equal to some momentum flux out of the surface of the volume we are considering. So the rate of change of momentum is equal to force. So the relevant force here is Lorentz force, which is given by this expression. And this force, the Lorentz force, the total Lorentz force, which can be given by this integral, is actually equal to the rate of change of total mechanical momentum of all the particles inside this volume V. Um, in the expression of Lorentz force for one particle, we know that this is Q into E plus V cross B. And for a distribution of charge, we can write Q as for element charge, we can write it as rho, and rho times V will be J, the current density, and we can integrate over whole volume to get the rate of change of total mechanical momentum. Now, for rho, we can substitute epsilon naught times divergence of E, and J equals to 1 upon mu naught times curl of B minus epsilon naught times d by dt. And we get this from Maxwell's equations. Now, after we substitute, our integrand becomes this. This term in epsilon times this term in square brackets. Now we can write B cross del E by del T as minus of minus of partial derivative of E cross B with respect to time plus E cross del V by del T. We can write this because this partial derivative of E cross B with respect to time, we can expand it using product rule, and it will give del E by del T cross B plus E cross del V by del T. And there's a negative sign here. And if we add E cross del V by del T to that, then we will get minus of del E by del T cross B. And we can change the order of this term in cross product, and the minus sign will go, and we will get B cross del E by del T. Now, in this expression on the right hand side, we have del V by del T, and using Maxwell's equation, we know that del V by del T is equals to minus of del cross B. So we'll get a minus sign here as well. Now we substitute for B cross del E by del T. We substitute this expression um, in this square bracket here, and we also add C cross B times divergence of B. We can add this because divergence of B is zero anyway. So we want to add this to make uh, expression of terms in which B occurs similar to uh, terms in which E occurs. So now we can see that we have similar uh, similar looking expression for B as well. Now integrand becomes this. We just take this partial derivative is equal to tan out here, and now we can integrate over whole volume. So this will be the same dp max by dt, rate of change of mechanical momentum, and the integral over this term we can take it on left hand side, and on the right hand side we have this expression in square box with um, we are doing integral over whole volume for this expression, and this expression is um, similar for E and B terms. So we can see we want to arrive at an equation which gives the rate of change of mechanical momentum plus rate of change of electromagnetic momentum equals to some momentum flux. So we already have rate of change of mechanical momentum, and we also have another um, time rate, another time derivative, and we tentatively call this um, term in this integral as p field, as this is the only derivative with respect to time which we can relate to rate. And this expression on the RHS, we will have to show that this is some sort of momentum flux. This is a momentum flux. Uh, we will have to prove this so that our assumption, tentative consideration of this, saying this as mm, momentum of the electromagnetic field is correct. And we can write B as mu naught times H. So this is actually E cross H is Poynting's vector. So mm, momentum of the electromagnetic field is actually proportional to the volume integral of Poynting's vector. So now to see that when we assume that this is P field, we will get the equation of the kind we want. We will look at the integrand, and we will look at only the terms which contain E, because expression of B is very similar. Now we are considering the first Cartesian component of this whole vector, and when we expand this out, we can see that divergence of E is multiplied with E vector. So when we take the first component, it will be E1 times divergence of E, and then we have this cross product term. When we want to write we want to write the first component of it, so the first component will be the second component of the first term, which is E2 times third component of the second term, which is del cross E, minus third component of the second term multiplied with second component of the third term, second component of the second term, third component of the first term multiplied with second component of the second term. And we need to change the signs because there is an overall minus sign here. So after that, we will again uh, write this cross product del cross E. We will write the third component of this cross product del cross E, which can be given by this expression del E2 by del x1 minus del E1 by del x2. Similarly, you can write the second component of this del cross E, which is del E1 upon del E1 by del x3 minus del E3 by del x1. Now we just multiply all these terms, and when you multiply even with we multiply even with del E1 by del x1, so we can write it as half of del E1 square by del x1, and we can see we have written here, and we have subtracted well, the factor of half is not here because we have subtracted half of del E1 square by del x1 here as well. So that gives us half of del E1 square by del x1. And if you multiply, when you multiply E1 with del E2 by del x2, plus we also have E2 times del E1 by del x2. So we can write it in some compact form with um, uh, partial derivative of E1 times E2 with respect to x2, because when we expand it using product rule, it will give the same as we had in the equation 2.11. And similarly for we have E1 multiplied with E3, and you will also have E1 multiplied with partial derivative of E3 with respect to x3, and here we have um, mm, partial derivative of E3 times partial derivative of E1 time partial derivative of E1 with respect to x3. So we get this, and we also have E2 times del E2 by del x1, which we can write as half of partial derivative of E2 square with respect to x1, and we will also have see a similar term for E3. So E3 times del E3 by del x1 can be written as half of del E3 square by del x1, which we can see here, these terms here we have written. Now, this was the first component of this vector. Now you want to write any general component, say alpha component. Uh, we see that we can write it in this form of in this summation form. We can see this whether it matches or not by putting alpha equal to 1. So when you put alpha equal to 1 here, um, we have summation over beta, partial derivative with respect to x beta of E1 times E beta minus of half of dot product of E with itself times Kronecker delta 1 beta, 1 comma beta. So beta beta range of beta is from 1 to 3. So when you put beta equal to 1, the Kronecker delta will be 1, and we will have minus of half e square, which is e1 square plus e2 square plus e3 square, and we also have this um, del e1 square by del x1 square, which is this term. So we have this term by putting beta equal to 1. Now when you put beta equal to 2, Kronecker delta will be 0, and we will be left only with del e1 e2 by del x2, which is this term. Now when you put beta equal to 3, same story. Kronecker delta will be 0, and we will be left with del e1 a partial derivative of e1 times e3 with respect to x3, which is given here. So for alpha equal to 1, we see that it matches. So we are sure that for any general component, it will be like, it can be written like this. So now, uh, for a vector k, for any general vector k, divergence can be written in summation form as this: partial derivative of k alpha with respect to x alpha and summation over alpha. So the divergence of a vector is actually giving us a scaling. But in equation 2.13, we have on RHS of equation 2.13 and RHS of equation 2.14, we can see some similarity here. We have summation over alpha here. We have summation over beta here. We have partial derivative with respect to x alpha. We have partial derivative with respect to x beta. So This looks like divergence, but we also have some E alpha here, so which we are specifying by choosing which component we want to write. Um, so alpha equal to 1 to 3, there are three components. So this quantity in equation 2.14, the quantity on RHS are actually which are being differentiated with respect to X alpha are components of a vector. But here we have two indices, alpha and beta. And when we are taking derivative with respect to beta only, it is, and we can vary alpha from 1 to 3, it is giving us three components. So it is not a scalar, whichever quantity we have on. These are not components of a scale, not components of a vector, right? Because we still have, we can still choose a degree of freedom with alpha, what you want to choose. So this is actually divergence of a um, second rank tensor. Divergence of the second rank tensor is a vector. So when we can write this um, vector in equation 2.13, this is a vector for which we are taking the alpha component only here. So then a divergence of a second rank tensor gives us a vector. Here we have considered only the terms which contained E, and for B we will also get a similar thing. We will also get a second rank tensor. Um, because the equation, because the terms containing B were very similar to the terms containing E. And so if we want to write this in vector form, combining the components of the terms with E and terms with B, we will get a second rank tensor called the Maxwell stress tensor, T alpha beta. These are the components, and these components can be given by this epsilon times this square bracket. Here we have this the term in bracket here, and we also have magnetic field components. So the equation that we had earlier here, we can write this um, highlighted term in terms of Maxwell's stress tensor, the components of Maxwell's stress tensor, which are differentiated with respect to x beta and summated over, so and we have summation over beta. So the um, alpha component of the rate of change of total momentum, that is P max plus P field, can be given as um, volume integral of summation over beta partial derivative of T alpha beta with respect to x beta. So for any vector k, we have divergence theorem, which says that volume integral of divergence of any vector is equal to surface integral of that vector dotted with the normal component of surface area vector, small area, element area d. Um, we can write divergence as summation. In summation form, we can write divergence as this, as we have already seen. And this dot product we can also write in summation form as summation over beta, k beta, and beta. So in equation 2.16 on the RHS, we have something similar to what we can see in the LHS of equation 2.18. It's just that it is T alpha beta here, it's K beta here, and it's T alpha beta here. So we can apply the divergence theorem here for alpha component because we are considering only alpha component here, and we can get T alpha beta and beta dA summation over beta and surface integral. So what this says is that the rate of change of total momentum, the alpha component of it, can be given by surface integral of summation over T alpha beta and beta, and n is the normal vector, outward normal vector to the surface. So this is what we intended to achieve. We have written the rate of change of mechanical momentum plus rate of change of um, momentum of the electromagnetic field in terms of some um, flux leaving the surface area, which is the momentum flux. So this quantity here, um, summation over beta, T alpha beta and beta is the alpha component per unit area of momentum flowing across the surface S into or out of the volume V. And the rate of change of momentum is force. So we can also say that this is the force per unit area transmitted across the surface and acting on the system of particles and fields inside the volume. This is the alpha component of the force, we should say. So this is the conservation of momentum of system of charged particles and electromagnetic fields.
So, first of all, this electromagnetic force in medium is not same as uh, electromagnetic force in free space, because we can see there is P over here, polarization and magnetization. So in medium, when electric field or magnetic field pass, it leads to polarization and magnetization of medium. So this expression for force is not same as Lorentz force in free space, uh, and these Maxwell's equations also get modified. You can see there is T What is D? And then D is epsilon naught E plus polarization. So we can see polarization and magnetization are inbuilt in this Maxwell's 4 equation, and similarly we can see H over here. So and B. B is mu naught times H plus M. So we can see polarization and magnetizations are inbuilt in this Maxwell's 4 equation. So now these are the equations that I was talking about. Uh, this is D equals epsilon T plus B, and B equals mu naught times magnetic field plus magnetization, where P is polarization and E is electric field. This is a special case, and we are not going to use this thing. This is true for only linear dielectrics, which is special case. We are solving for general medium. So we just want to simplify the force expression. Like we can see there is a term like P dotted with nebula, so and M dotted with nebula. So we just want to replace them. So we're going to use this identity uh, and we just replace P dotted with nebula times electric field with the right hand side plus this term. And similarly we replace magnetization dotted with nebula times uh, magnetic field with this right hand side plus this term minus this term. And uh, so we know we have this expression for P. So we just take a dot product both sides. So del dot D plus equals epsilon naught del dot E plus del dot P, and uh, we assume that there is no any free charge density. So del dot D is 0. So what is del dot P? So del dot P is minus times epsilon naught del dot E, and similarly we do for the magnetization. Del dot M is del dot B minus mu naught del dot H, and we know that this magnetic field is magnetic induction is divergenceless, so del dot B is 0 from Maxwell's equation, and so del dot M is minus mu naught times del dot H. So we just substitute these values for del dot M and del dot P in these two equations, uh, and so we just will get some simplified expression for these two terms, first two term, and then we're gonna simplify the next two, third and fourth term as well. So we just replace this P with uh, D minus epsilon naught E, and M with B minus mu naught H, and uh, we will simplify them, and here it is. We just replace with we just replace P with polarization with D minus epsilon naught T, and we simplified this expression, and we finally get this. Similarly, we will do for magnetization as well. We replace M with B minus mu naught H, and we will get this expression finally. As we will see, why we are doing this simplification, because after doing that we'll finally get the expression for force, which is these terms minus times this. If we will shift this term, that 1 by c square uh, del E cross H by del T to left hand side. This is the final expression for force, and we can see that this FRT is the force expression is rate of change of total momentum, mechanical momentum, and the second expression is rate of change of electromagnetic momentum, and which is equals to this right hand side. And we can see the first four term is say which is, the first four terms are very similar to what we have in free space. Only these three terms are extra here, and we can see if we put p equals 0 and m equals 0, so px py pz is 0 and mx my mc is 0. So this three terms will get vanished, and similarly we can replace then if m is 0, so mu naught times h is just b. So if we replace these three terms are 0 and we replace mu naught times h with b, we'll get the same equation what we have in free space, which is most probably explained by Gopal. So this we can see if polarization is 0, so d is just epsilon of t, and b is just mu naught times h. And so the only change over here is in medium this electric field this electric field and magnetic field means these fields will cause magnetization and polarization in medium, which will appear which are appearing in this force expression, and which is obvious because this electric will interact with polarization and magnetic will interact with magnetization, and hence they will contribute to this force expression, and this is what we finally got. We, we'll get again we will find this right hand side is just a electromagnetic stress tensor in uh, yeah, if we simplify this, this is rate of change of the first term. F is rate of change of mechanical momentum. Second term is rate of change of electromagnetic momentum, and this is equals to the right hand side. And we saw the first four terms are just same as which first four terms are similar to what we have in free space. The only these three terms are if we have medium, these three extra terms will be here, and we saw that if we put p polarization and to be 0 and magnetization to be 0, we will recover what we have what we had in uh, free space. So uh, this is what we have. Uh, so in medium, this p and m are not 0 in general. So this is general expression for force in medium, and um, after this Kabir will explain how to get the electromagnetic stress tensor from this equation, and we saw that as these three terms are introduced, these three extra terms are introduced in medium, so they will definitely affect the electromagnetic stress tensor. Uh, Means there will be some extra term in electromagnetic stress tensor, uh, which we have in free space. So that's all. After this, Kabir will explain how to get the stress tensor of electromagnetic stress tensor in medium. and that is it.
Okay, so I'll go through the example number 2 of the paper. So we have a linear isotropic homogeneous medium with with electrical permittivity epsilon and magnetic permeability mu. Uh, and we have passed a collimated monochromatic beam of light propagating in the x-axis direction. The beam has an electric field amplitude E naught along the x-axis and the magnetic field amplitude H naught along the y-axis. And the relation between the E naught and H naught is given by this, where Z naught is impedance of free space, which is not is equal to root over of epsilon naught upon naught. Additionally, there is Ez component of the electric field, that is odd function of x, which goes to 0 at the center of the beam. So the time averaged rate of flow with x momentum along the x-axis at the central yz plane is given by this. So we'll prove it. We have this txs which we have proved earlier. In this we have ey 0, ez is also 0 as it's goes to 0 at the center of the beam. Hz is also 0 and Bx is 0. And Tx from paper we have Tx is equal to epsilon naught epsilon Ex and Bx is equal to mu naught mu Hx. And as we have done Ey and Ez 0. Then when we put these things into dx into this equation, we'll get a minus half epsilon inverse epsilon naught epsilon Ex the whole square. And then in the place of hy we have this hy relation, then we have this relation given, which is this, rearranging squaring the term and and then rearranging it to get this. So we have took epsilon naught common and Ex square common. Then since the beam is linearly polarized with the electric field amplitude along the x-axis, we can replace Ex square with E naught square, which will give this thing. And taking the average of the thing would give an extra half factor due to the sinusoidal nature of the fields. So we got Txx average value of Txx. Then the momentum flow is can be entirely converted into the two forces. First is the force on the electric dipole just above the x-axis, and the second force, which we denote by FSW, which is exerted on the medium by the upper side wall of the beam. First we will try to find the force on the dipole. So to do this, we'll take a gap between the in the middle of the beam, and this, and we will find the force using the continuity of d perpendicular. So let's say we have the field E naught, the gap field would be E naught epsilon naught E naught, which will give epsilon E naught over here. Then the average electric field at the interface would be E naught epsilon E naught plus E naught by 2, which is this. And the gradient would be similarly epsilon minus 1 E naught by 2. So let's denote it by C, this by A. So the field gradient is this. Uh, then we'll try to find the so the dipole density is B would be epsilon naught epsilon minus 1 E naught x square in the x direction, and the force is given as P into gradient P into E P into gradient of E, which would be epsilon naught epsilon minus 1 E naught into epsilon minus 1 E naught divided by 2, which will give us this relation. Taking the average of the fx will yield this. Then we have to find the sidewall force density. So the sidewall force density in the average term would, would be equal to dxx plus this force fx. So let's see if we can get this. Dxx is this half epsilon naught epsilon by mu minus epsilon square E naught square, and this half epsilon naught squaring epsilon minus 1 term, which will give is epsilon square plus 1 minus 2 epsilon minus 2 epsilon into E naught square. Cancel the square term and taking out the common 1 by 4 epsilon naught term, epsilon by mu minus 2 epsilon plus 1 E naught square, which will give us this force on the sidewall. Thank you.
Good morning everyone, this is Adarsh. So today we are going to discuss this research paper by the title Electromagnetic Tensor in the Ponderable Media, and I am going to discuss the example 3 of this paper, in which we take the given condition accordingly. So this problem example 3 is combination of example 1 example 2 with a slight variation that in this the beam that the collimated monochromatic beam that we are passing, it's situated at an angle theta with the z-axis. So the beam propagates in the xy plane taking an angle theta with the z-axis, and also we have the finite diameter for this beam and finite width. So due to which, so as this beam has theta angle with respect to their axis, the footprint of this beam on the x-axis is of unit length, and the component of the width component, like you can see in this figure, is cos theta for this beam since the beam is of unit length. And also we have this is electromagnetic components, electromagnetic field components of this beam, which are EX, EB and Fy. Apart from that, we have set the Fx, dB equal to 0, and the dB is epsilon EB that we have got from the earlier derivation. Now in this problem we are going to find out about the expression for the rate of momentum flow from the stress center, and also from the combination of like also from the things we derived in example 1 and 2, combining them and proving that the thing we got from directly from the stress center component and the one we got from the combining all forces is same. So from this figure you can see that we have sidewall force acting here on the top and bottom, and apart from that we also have force due to force on electric dipole due to electric on boundary due to electric dipole, which we may see that the center of dipole is given by equal to epsilon e minus 1 e naught sin theta z dash. Since we have taken the component of electric field along z direction, and this is proportional to the electric field gradient. So we can write the force equation that having product of these two and taking its time average, we get this 1 by 4, and thus the effective force on the on the boundary due to the dipole layer is minus 1 by 4 epsilon of e minus 1 whole square e naught square sin square theta z dash. And also from the example 2 where we derived the force on side walls in the most simplified form, where these being side are being propagated at angle theta, and we utilize that expression of force on side walls from example 2, and we we can't directly implement that in this equation, so we take the components along x and v to derive the force on the boundary side wall for our equation, and take the time average of that as needed. Thus the force that comes is 1 by 4 epsilon naught in this square bracket. We have epsilon upon 2 to the power minus 2 epsilon minus 2e plus 1 e naught square sin theta minus cos theta x dash plus sin theta d dash. And also we have one more force due to the rate of flow of momentum, which is dt by dt, and for the cross section cos theta, and this is given by 1 by 4 epsilon naught 1 plus e upon mu e naught square cos theta sin theta x dash plus cos theta d dash. And we have assumed that the frequency of monochromatic plane wave is omega. That is from the example 1 where we use that, and there is no need of it since we have directly used the equation from the earlier example. So now we combine these all three forces and solve this thing. So, and this resulted in this beautiful expression, which is half epsilon naught e naught square epsilon cos theta sin theta x dash plus half cos square theta minus epsilon square sin square theta plus e upon mu theta. So now this is all by combining all the forces and taking some things of example 1 and 2 into account to find the rate of momentum flow. Now we would do this thing but would not use this method. We would directly use the components of the stress tensor that we had derived earlier, and we would be using DSG and DG. So, and do the time average of both of them to feel at a certain time average momentum flow. So you can see that from the earlier expression, the expression we derived for stress tensor, we take this as given, dHg is minus dH dV minus hh dV, and dV tensor component is half epsilon naught e square plus epsilon naught e y square minus 1 upon epsilon naught dV square plus half mu naught hh square plus mu naught hy square minus 1 upon mu naught dV square. And we have also taken, we only have these three electromagnetic field components for our electric field. So the components that we don't have, we have assumed it to be 0, and this expression which we derived from earlier, we use this, and we put hh equal to 0 and dv equal to 0, we result this thing to 0, and we have expression for hy square, which we are going to put further. You can see here that hy is under root mu naught under root epsilon naught mu naught mu naught. So PGG, the expression here, we write this in this way, half epsilon naught dh square plus mu naught dy square minus 1 upon epsilon naught dg square plus half mu naught hs square plus mu naught hr square minus 1 upon mu naught v is same. So we substitute these things in here, and we combine both these tensor equation for time average with x cap and v cap component, previously x cap plus v with v cap, which results in this expression. Now we substitute our relation that we found earlier, like since our electricity lies EH and ET component, and it makes a theta angle with respect to EH2. This gives us that EH would be E naught cos theta and ET would be E naught sin theta, and EV, as we know from earlier, is E naught E naught. Sorry, E naught and we substitute these things in the above expression and calculate the time average of it. Thus this results into this final expression, half epsilon naught E naught square epsilon cos theta sin theta square plus half cos square theta minus epsilon square sin square theta, so T upon me is that. And thus now we can see that the momentum flow, like the rate of momentum flow that we have got from both of solving, like both of these approaches, as relate the same thing. Thus we can justify and say that we can use stress tensor for calculating our thing in a, for a general, any general